Okay, so what is big O notation? So big O notation basically helps us pick the best algorithm or function or whatever you want to call it to perform a certain situation. So for example, in sorting algorithms, we have a bubble sort, we have a selection sort, and we have an insertion sort. Or in terms of for loops, we have just a regular for loop that would increment and have like a statement. Or we would have a for loop that would either multiply or divide at the index. So basically, each of these have certain time complexities. So for example, this for loop is big O of n. This one is big O of log of n. So in terms of big O notation, we can look at each of these different programs and we can decide which one to pick based on the big O or time complexity. So the best big O is big O of 1, which is constant time. So that doesn't depend on the size of, or the input size. So that means something like int I is equal to 0. So this integer I will always be 0. It doesn't depend on an input that will make it bigger or smaller, unlike, for example, this for loop. So in this situation, if we have these two for loops to choose from, we will choose from the log of n because it is a faster program in terms of time complexity using big O instead of this right here. In terms of sorting, insertion sort is big O of n in its best situations, while a bubble sort is big O of n squared in both best and worst cases. So using this information, we can use whichever sorting algorithm we want to decide which program will run faster. So in this case, we will go with the insertion sort instead of the bubble sort. And in this scenario, we will go with this for loop because it runs faster than this one. But obviously, the best situation is constant time. So that's really all big O notation is. It helps you compare different algorithms and different functions and see which one would run faster compared to the other. Okay, so these are the different functions that I have comparing different big O notation. So starting off, we have a recursive function that just shrinks the size randomly, calling two different return passes. This recursive function is going to be big O of 2 root n. Then moving on, we have big O of n factorial. This is the worst big O that you could possibly have. And a common algorithm that uses this is BOGO sort. So basically BOGO sort, right here, as you can see, we have the array and then we have the size that it takes from the parameters. And basically it's going to say, while array at index I is less than array at index I minus 1, which basically means the array is not sorted, then it's just going to go and pick a random index pretty much and swap at that index. So basically it's just a swap that has no meaning, and obviously the array is not going to be sorted, so it's just going to keep going and going and going and growing with the size. Moving on, we have, here's my linked list class. So just the normal stuff, inserting, removing, and then I have the two bubble sorts that I did. So here's the CPP file. So starting off, any insert and remove functions are going to be big O of 1 because they're constant. They don't depend on the size. And as you know, big O of 1 is the best possible big O notation in terms of time complexity that we could use. So these two functions, insert at end and remove at end, are both going to be big O of 1. And then we have the bubble sort version 2. So the best case for this bubble sort is big O of n, and that's because it has, unlike just a normal bubble sort, this bubble sort has a boolean called swapped, which basically only swaps if necessary. So compared to like a normal bubble sort, it'll have less swaps, and in the best case scenario, it won't make as many swaps or even 0 swaps compared to just like a normal bubble sort. And because of that, the best case scenario is big O of n. The worst case scenario is still big O of n squared, but since the best case scenario is big O of n, this is why I use bubble sort version 2. And obviously, as you can see, this is just using the linked list, so I have the size variable, and I essentially set swapped equal to false, temp equal to head, and then I go through the for loop and I say if at temp the next value is greater, if the temp's value is greater than the next value, then we make the swap. And obviously if temp is the head in the swap, then head becomes temp 2 because temp gets swapped, so it moves up a place, and then swap becomes true, and then we traverse through the linked list, and then obviously here's a check, and then if swap is false, then we break. So here we have just a normal bubble sort, so both the worst and best cases for this are big O of n squared. And here, as you can see, I didn't like a recursive function. So we have temp at head, we traverse through the list, and if the value is greater than the next value, then we make the swap because we want to sort in ascending order in this case. And same thing, if it moved up a value, then head is temp then. And else we traverse through the list, moving to the next list, and then we return the bubble sort head and the size -1 because that's our base case right here. And that's the print function. So that is 1, 2, and 3 functions using linked lists, and then 1, 2, and oh yeah, I forgot to mention this one. So this is the for loop. So since it goes at I is equal to I times 3, there's gonna be big O log base 3 of n, and this is the second fastest time complexity. This is the second worst, and then this is the worst overall. That's it.